Hi folks, welcome to another lesson, and this is going to be a new topic which is based on waves. So as usual when we start a new topic, there's going to be a lot of new terms for you to learn and some really basic ideas to get your head round before we move on to the actual higher content. Um, so for this lesson we're going to look at examples of coherent and waves, and use the word coherent and phase to describe waves, describe how constructive and destructive interference occurs, and we're going to state Young's double slit experiment is an example of interference of waves, say that Young's double slit experiment and interference is proof that light exists as waves, and also talk a little bit about what Young's double slit experiment is. So, a few things obviously you might remember from National 5, which are the basic characteristics of waves. So pause the video and try and remember what these missing terms are. Okay, so hopefully you got that the wavelength is from peak to peak or from trough to trough, and this wavelength is the same, it doesn't matter which one you measure it from, and it's always in meters. Another way to measure the wavelength would be if you start from one point and you end up along the same point a bit further along, that's a wavelength. So here, the sine wave I traced out is a wavelength, or you could trace out this cosine wave, which is also a wavelength. The other thing you need to know about was the amplitude, and remember the amplitude is from the middle of the wave to the peak, or the middle of the wave to the trough. And that the amplitude measures the energy of a wave. Okay, so there are some of the terms. Okay, another thing as well is that waves also have a frequency, which is the number of complete waves per second, and a velocity, and they're related by this equation, V is equal to F lambda. And you need to know this equation, it's in your equation sheet, because we will be using calculations using these equations later on. So let's get to some terminology. So I would like you to make a note of this now. Your assignment will be to summarize all of these terms. So you might want to write these out on a separate bit of paper and then submit that as your assignment. So waves are in phase if the crest meets a crest or a trough meets a trough, or if they're one wavelength out of step. And the one that I really want you to try and remember is actually this second one here. This first one is really handy if you're going to draw it, and I would recommend you draw it, but the one wavelength out of step is a bit more rigorous, a bit more formal. Now, what do I mean by crest meets a crest or a trough meets a trough? Well, here's a wee diagram. You can see I've got two separate waves here, and if you line them up properly, then you can see a crest meets a crest, a trough meets a trough, so these two waves are in phase. So out of phase, well, it's really the opposite of in a phase, I suppose. And this is where the crest meets a trough and they are half a wavelength out. And again, I would like to try and remember this one here, because this is actually the one that's more formal and more useful later on. Again, what do I mean by crest meets a trough? Well, if you've got two waves lined up, we can see here a first wave and a second wave, that they're almost like the opposite of each other, because here, when we line them up, then we've got a crest meeting a trough. So you can see there's a crest and a trough and a crest. So that means they're out of phase. Now, coherence is another term I want to learn, so make a note of this, please. Waves are coherent if they have a constant phase difference, i.e. the same velocity, wavelength, and frequency. An example of a coherent light source is a laser. The opposite of coherent is an incoherent wave, and this is when the phase difference is different and they have a different velocity, wavelength, and frequency. An example of this is the light emitted by a light bulb. So it really ties in with this idea of phase and out of phase. Coherent waves are generally in phase, incoherent waves are generally out of phase. And this is a wee diagram just to show you that we have white light, light from a light bulb could be made from the whole range of the colours of the spectrum. So that's why it's definitely incoherent and out of phase. Monochromatic light source, remember monochromatic means a single light or a single colour of light. So they could be in phase, but they could also be out of phase. Just because they're the same colour doesn't mean they have to be in phase. And a laser is a special one. It's the only one where it's a monochromatic light source. You only have one color of light, and they are all in phase, so it's coherent. So be able to tell me an example of a coherent, incoherent wave before I move on. Now, interference is a wave phenomena that only occurs with waves. So this is how we can tell something is a wave, is that it undergoes interference. It was the original evidence that light exists as a wave. So again, this is a wee bit of knowledge that I want you to know, and it's really important that you remember this. There are two types of interference, constructive and destructive. And you can probably figure out what these means judging by the names of these two types of interference. Now, there is a nice wee demo that goes with this. However, it's a simulation, so I'm going to show you this at the tutorial, and I'll probably upload a video later on in the week to show you the simulation. So examples of everyday interference are, again, this is where the simulation comes in. If you've ever tried to set up two speakers, then what you might find is that depending on how far apart you put the speakers, and if you walk from one speaker to the next one, you'll find that you get patterns of loud and quiet noises. So what I'm going to try and do is I'll try and record that for you and upload it. It is quite a big file, so I'll see what I can do, folks. Now, what is constructive and destructive interference? So, waves can interact via interference. So, that's one of the key terms that I want to use. And I really want to start using these terms like in phase, out of phase, coherent, incoherent, monochromatic, and interference. So, in phase waves will interfere constructively. So, one way to describe this is where you've got two waves that are in phase. So remember, in phase means that they are exactly one wavelength apart or zero wavelengths apart, because it's really the same thing. And that another way to think about it is that the crest meets the crest. Now, you can think about if you were to add these two waves together, you could probably think, well, if I add the two waves and they're exactly lined up, then I'm very likely going to get a much bigger wave. Okay, and that's essentially what happens in constructive interference, is that your amplitude, the energy of the waves, will combine and you get a much more energetic wave. So for example, if these were two sound waves, then if they interfere constructively, then you would hear that sound become louder. Okay, so just to summarize that, and again, I'd like you to write down the previous slide and this one. I'm afraid there is a lot of note taking because we are doing sort of the basic knowledge here. The resultant wave will have an amplitude that is the sum of the individual amplitudes. So that's the net result of constructive interference. One thing to remember is that even though the amplitude increases, the frequency stays the same. We're not changing the frequency, and this can be quite confusing if you're listening to sound waves that interfere constructively, because some people tend to think when it gets louder that the frequency has changed. It's not, it's just got a louder sound. And this is what we call constructive interference. Now, you are expected to explain how constructive interference happens and what the effect of it is. So my recommendation to you is if you're asked to explain constructive interference, I would draw the diagram like this, and then I would explain what in phase means, and then I would explain how constructive interference means that the resultant wave will have an amplitude that is the sum of the individual amplitudes. So this slide here, I would say, is probably the most important one because it's how you would, it's a model answer, if you like, for explaining constructive interference. Now, moving on, you can probably figure this out for yourself, that out of phase waves will interfere destructively. And you can probably guess that if you've got two waves that are out of phase, so they're half a wavelength out, remember, or if their crest meets a trough, then you can imagine if you combine these together, they will basically just cancel each other out. Now, what that means is your sound, if it was a sound wave, would go from a reasonable level of sound to basically being very, very quiet because essentially you've cut out the waves. And you can use this technology to make noise cancelling headphones, although there is a lot more physics behind it than that. So again, this is a really important slide that I want you to take note of, which is these waves can combine to cancel each other. So again, the frequency stays the same if the wave is still there, and this is called destructive interference. So again, for the model answer, you have the diagram, which we'd highly recommend you draw, and then you have the word description here to explain your diagram. So how can we explain or visualize interference? Well, one way to think about this is in terms of something called the wavefront. So if we imagine and think about if you've ever dropped a pebble or a rock into a pond, or even if you've seen like maybe water dripping into a basin, you'll notice that you have a point where the wave originates, and as the wave spreads out, it spreads out in these kind of wee circlets. Okay, so we call these wee kind of circles as a wavefront, and they spread out equally at the same speed. And all that means is that you get a lovely circle which has a certain radius that's the same all the way round. And that's one way to think about how a wave propagates. And propagates means it spreads out. So how can we show interference just by using one source? Now, we've talked about interference of two waves, and generally that's in the case of two sound waves coming from two separate speakers. Can we do it with only a single wave? And the answer, of course, is yes. So to do this, we provide a second source of light by splitting a single source using something called a grating. And this is what a grating looks like. Now, these gratings are actually a bit more than we need, and we're going to talk about this a lot later on in another lesson called diffraction gratings. But the one we're going to be used is one which doesn't have as many gratings in a line, sorry, which has only just got a double slit. So actually it only has two slits. So this one is called Young's double slit experiment. And as you can see, this is our grating here, and we only have two slits there. Now, for the experiment, we use a monochromatic coherent light source, e.g. a laser. And if we were in class, I would show this experiment to you. It's shone at a double slit. This makes a single source into a double source of light. So from a single wavefront, we now have two wavefronts. So we're going to show you what that looks like in a couple of slides. Now, when the light is incident on two small slits, the wavefront is divided by each slit and acts as a secondary source. This allows interference to occur. And this is just a fancy way of saying we've got one wavefront. When it gets to the two slits, separates or divides into two wavefronts. And that allows interference to happen because you can think of these two slits here as being like your two speakers. Each of these have a source of waves coming out of them. And if you've got two sources of waves, they can either be in phase or out of phase. You can either get constructive or destructive interference. And what you would see is that on a screen, you would see a pattern of fringes which are light, dark, light, dark. And I'll try and show you this on the simulation. Now, this is what it would look like in real life. You can see here, if we ignore these ones here, if we just look at this central band here, you can see you've got a very bright fringe, and then you've got a dark fringe, a bright one, a dark one, and a bright one. So wherever we have a bright fringe, this is where we get constructive interference. Wherever we have a dark fringe, that's where we get destructive interference. And you can see that this repeats throughout the whole band, but the bands themselves, you can see we've got a separate band here and a separate band here, but these themselves also seem to be a little bit fainter as we move further away from the center of this diagram. So there's a lot happening there, but all I want you to be able to see is that if you have a double slit separating your waves into two waves, you then get this interference pattern of bright and dark fringes. Okay, now this is another diagram to show you how this interference pattern happens. So if you imagine this is our wave coming down the way, and this is just a single wave from our laser. Remember, the wave spreads out like a wavefront. So as they hit this wavefront, the grating here, sorry, you've got two slits, so the waves squeeze through, and that essentially gives you two wavefronts. Now, as these two wavefronts spread out, you can see Where they overlap, you can get areas of constructive and destructive interference. And then as these wavefronts hit the screen, you get this kind of banding appearing. So the double slit will split our single source of light into two separate sources of light. These can then interfere with each other. So what type of question might you be asked about this? Well, a student investigates interference of light by directing laser light of wavelength 630 nanometers onto a grating as shown below. So a pattern of bright spots is observed on a screen. Explain in terms of waves how bright spots are produced on the screen. And this is only worth 1 mark, but what I would expect in your answer is you using the terminology of in phase, out of phase, constructive interference, destructive interference, and probably draw a diagram. So how would we answer this question? Well, here's our model answer. Waves meet in phase, or crest meets crest, so that's really saying the same thing. Trough meets trough, and then the path is equal to m lambda. Now, don't worry about this bit because we're going to do later on, but what I would expect to say is this top bit here, and probably draw a diagram. And the other thing I would like you to do is to actually explain this word in phase, because if you're using a technical word, you should really explain it. So for me, the answer must be waves meet in phase. In phase means that the crest meets a crest, so you could draw a diagram like this, or you could say that they are one wavelength apart, and when they combine together, that means you get a wave which has a resultant amplitude that's the sum of the two separate waves. So that's how you would answer that as a model answer. Make sure you're comfortable with the answer here. Don't worry too much about this because you can answer the question just by saying these 3 statements here, or one of these 3 statements, or draw the diagram.